Bismillahirrahmanirrahim. Assalamu alaikum dear students. We are now starting the second lecture for week number 6 for our course of communication systems. In our first lecture we had a discussion regarding the time domain representation of frequency modulated signal and phase modulated signal. We discussed some fundamental terms related to FM and PM signals as well as their time domain representation and their relationship with respect to their instantaneous phase and instantaneous frequency. In today's discussion, we'll be performing some spectrum analysis of the signals, phase modulated signal, but as we know that the phase modulated signal and frequency modulated signal, they are closely related and has similar representation. The same discussion that we'll be doing in this lecture will be applicable to both phase and frequency modulated signal. In general, if you try to derive a generalized results for the spectrum of phase and frequency modulated signal, we would notice that the spectrum analysis is not straightforward. Rather, the modulated signal spectrum would be very complicated and cannot do an analytical analysis to encompass the spectrum of all cases for the signal. In the absence of this general analysis, we can analyze the spectrum with the special cases which are shown here. So we'll be discussing two special cases and then we'll try to generalize the result in order to have a sufficient bandwidth criteria for base FM and PM signals. So for this analysis, first we will consider a narrowband case. A narrowband case is the one where we have small deviations. The phase deviation is considerably small, and in that case we will be having a relatively small band. That's why we call it a narrowband case. For the wideband case, as I mentioned, that generalized analysis is not very easy. In that case, we will analyze the wideband case by using a tone modulation. Tone modulation means we will be considering a sinusoidal message signal of a single frequency. So there will be a single frequency sinusoidal signal, and by using that sinusoidal message signal, we'll try to derive some relationships related to the bandwidth of FM and PM signals. So from that we can also derive the narrowband width of signal and also the wideband bandwidth signals. Although these two are special cases, but with those special cases we will be able to comprehend significantly the spectrum of the FM and PM signal, and we will be able to calculate the bandwidth of phase modulated and FM modulated signals. So let us start our discussion with narrowband FM and PM signal. So narrowband FM and PM signal means the phase deviation is small. So phi t, the changes in the phase, they are considerably small. So we take it as phi t is much smaller than 1 radian. Okay, so this is the mathematical case for the narrowband PM and FM signal. The modulated signal for this particular case can be represented like this, as we have discussed in our time domain representation as well. Xt is AC cos omega ct plus phi t, where this phi t contains the message information. You can see that this relationship is a simple relationship where you have cosine and sum of two angles. Cosine alpha plus beta is a commonly used formula in trigonometry. So if you expand this relationship with cosine alpha plus beta formula, you would see that you will get two terms. One would involve cos omega ct and second would involve sin omega ct. The cos omega ct would have a coefficient of AC cos omega phi t, whereas the sin omega ct would have a coefficient of AC sin omega sin phi t. So you can see that in fact this modulated signal is actually a combination of two components, which are cosine component and sine component. In communication terminology, these components are named as in phase and quadrature component. So this cosine component, this is actually the in phase component. You can see this I represented here. I is for in phase. So this in phase component is given by AC cos phi t, whereas this Q here, it shows the quadrature component or the sine component, and mathematically this component comes out to be AC sin phi t. So in practice, the modulated signal in both cases, FM and PM, it can be represented as in phase and quadrature components like this. So we choose this as our starting point here. So if we try to simplify these in phase and quadrature components with respect to our assumption where phi t is much smaller than 1, that is we are working on the case of narrowband PM and FM, in that case we can make some approximations to generally just to simplify this relationship. So you can see that this in phase component, which is AC cos phi t, this can be written as AC, and this is the Euler's expansion of cosine function cosine phi t, 1 minus phi square t upon 2 factorial plus similarly phi raised to power 4t upon 4 factorial, and so on. This goes on up to infinity. Similarly, the quadrature component can also be expanded by using Euler's identity, which is given here. So AC sin phi t can be expanded as AC, and sin phi t has its Euler's expansion, which is given as phi t minus phi cube t upon 3 factorial, plus then next term will be phi raised to power 5t upon 5 factorial, and so on. It will go up to infinity. And taking our assumption of narrowband FM and PM signal, that is this phi t is much smaller than 1, in that case this phi square t will be even smaller, and if you divide it by 2 factorial you will get an even smaller term. So in that case, because this phi t is taken as much smaller than 1, so I can ignore this term. Similarly, all higher order terms can also be ignored. So the only term that will be left here would be this 1, and once it's multiplied by AC, so you can approximate it by AC. So therefore this AC cos phi t for the case of narrowband PM and FM can be approximated as AC. Similarly, the quadrature component can also be approximated. You can see that sin phi t has this expansion, but because this phi t has the condition that phi t is much smaller than 1, in that case the higher order terms like phi cube t, it will be even smaller, and once you divide it by 3 factorial you will get an even smaller term. So this phi cube t by 3 factorial would be a much smaller term as compared to phi t, and similarly all other terms would be even smaller. So in that case we can conveniently ignore all the higher order terms, so you will be left with only one term, which is phi t, and once it's multiplied by AC, so the approximate value of this function would comes out to be AC phi t. So therefore quadrature component can be written as can be approximated as AC phi t. If we substitute these approximate value in the original expression here, so you can see that this modulated signal XCT can be written as AC cos phi t, because this XCI, the I component is actually simply AC, whereas this quadrature component is AC phi t. So you can substitute it here to get AC phi t sin omega ct. So this comes out to be the mathematical representation of this narrowband FM or PM signal, where the modulated signal is given as AC cos omega CT plus AC phi t sin omega CT. You can notice that the first term is actually the carrier, and this term phi t, which includes the message signal, and this is the actually 90-degree phase shifted carrier. So this is a part of carrier. If we try to plot the spectrum here, you can make an easy resemblance with the AM signal. If you recall, in AM signal we had a constant we have a carrier term and a product of message signal and the carrier. So you can see a simple analogy here, and if you try to make the spectrum of this signal, you would see that the carrier would be represented as simple impulse, whereas this second term phi t sin omega ct would have the spectrum of phi shifted to the carrier frequency. So it has the spectrum, this phi, capital Phi shows the spectrum of that phase phi t shifted to this high frequency phi minus phi fc. But we know that this phi t is actually dependent on the message signal, so the spectrum of phi f can be related to the message signal by this simple relationship, by taking simply the Fourier transform of this this phase of the modulated wave. So you can see that for PM signal, the spectrum of the phase can be written as phi delta into xf, where xf is actually the message signal spectrum. And for the case of FM, you can see that this spectrum comes out to be xf divided by this f, which is the frequency here, and multiplied by j f delta. So in both cases, for PM as well as for FM, you can see that the spectrum is dependent on the spectrum of xf. For PM, the spectrum is directly related to xf with a constant multiple here. For FM case, we have a constant multiple, but the spectrum is also divided by the frequency f. Here you can see that it's divided by the frequency. As we notice that the spectrum is directly related to the spectrum of the message signal, so of course, as we did for the AM signal, the spectrum would look similar to the message signal spectrum. Therefore, for the case of narrowband FM and PM signals, the bandwidth is approximated as 2W, where W is the bandwidth of the message signal. So this is an illustration of an amplitude spectrum of modulated signal. So if we have a spectrum, this one shows the spectrum of the message signal. So for the case of narrowband PM, narrowband phase modulation, you would see that we have a carrier term which is represented as a spike or as an impulse in the frequency, and we have a spectrum which looks similar to the spectrum of the message signal which is available here. For the case of narrowband FM, we have this spike of the message, the carrier, which is represented as an impulse. However, the spectrum is kind of different than the narrowband PM because of that division with the frequency, which is illustrated here. You can see that the division with the frequency is needed for FM spectrum. So you would see that as we go closer to the carrier frequency, in that case the spectrum amplitude would be increasing, so it goes towards this spike. However, if you notice that in both cases the bandwidth is same, you can see that the bandwidth starts from the this starting value of fc minus w and end at fc plus w. Similarly, for narrowband PM, the bandwidth starts from the fc minus w and ends at the fc plus w. And in both cases, the total bandwidth comes out to be 2w here, as I mentioned earlier. You can easily see that the narrowband PM and narrowband FM, they have the spectrum which resembles the AM spectrum. However, you should notice that this resemblance is in the amplitude spectrum only. The phase spectrums which are not plotted here, so phase spectrums are different as compared to the amplitude spectrum. So the bandwidth occupancy for the narrowband PM and narrowband FM is almost same as that of the AM signal. Let us now start the discussion related to the wideband case. As I mentioned, we cannot directly analyze the wideband signal, rather we will be having tone modulation as a special case, and then we'll try to analyze its behavior to get a generalized result. So let us consider an FM and PM modulation by using a sinusoidal signal. So I have assumed these sinusoidal signals here. I have taken AM sin omega mt for PM and AM cos omega mt for FM. Why I made these assumptions, different assumptions? This is because with this assumption the phi t definition would become same for PM and FM. So it will generally simplify the analysis, because we have made different definition for the tone signal, but with same beta FM the rest of the analysis would become same for both FM and PM. So how the result becomes same, it's illustrated here. We know that for PM signal phi t is represented as phi del xt. This variation is actually phi delta xt, and phi del xt is phi delta AM sin omega mt, which is assumed here that xt is AM sin omega mt. For simplicity, we take phi delta AM to be equal to beta. So beta is actually taken as phi delta AM for phase modulation here. Then for FM signal, you can see that for FM signal the phase is represented as 2 pi f delta integral of xt, and xt we have taken to be AM cosine omega mt. So if I simplify this, you can see that AM is a constant which is written here, and integral of cosine omega mt would be sin omega mt divided by omega m, and we know that omega m is 2 pi fm. So if I substitute by 2 pi fm, so this 2 pi would cancel and we would left with fm only. So this AM f delta upon fm, this can be written as beta. So we have for fm, beta is defined as AM f delta upon fm. So you can see that both cases the phi t has become same. Phi t is beta sin omega mt, where for PM phi t is again beta sin omega mt. However, we have different definitions of beta, which is named as modulation index. So modulation index is defined differently. So for PM, modulation index is phi delta AM. For FM, modulation index is AM f delta upon fm. One thing that you should notice is that in some cases, because we generally work on the normalized signal, in that case this AM would become equal to 0, that is the maximum amplitudes that can be achieved by this sinusoidal function would be taken as 1. So if you have that condition, in that case this PM and FM signal would have definition definition of beta, which will be given as phi delta. Beta would become equal to phi delta for PM, and beta will be equal to f delta upon fm for the frequency modulated signal. So we can some of the authors, they prefer to ignore AM by using the condition that AM is equal to 1. So let us now move on to the analysis. So this is our mathematical representation of the modulated signal. xct is equal to AC cos omega ct plus phi t. We can expand it by a simple cos alpha plus beta formula. You can see that it will come out to be AC cos phi t cos omega ct plus AC sin phi t sin omega ct. But phi t is now defined for the tone modulation as we have given here. The phi t is given as beta sine omega mt. So we can simply substitute the value of phi t here. So this phi t can be written as beta sine omega mt, and similarly this phi t can be written as beta sine omega mt. So let us first correlate this tone modulation with the narrowband FM and PM signals that we discussed previously. The narrowband case occurs when beta is much smaller than 1. For the case when the beta is smaller than 1, we can make an approximation to this expression. So this is cosine of beta sine omega mt, as beta is taken as much smaller than 1. In that case, this argument is a small number, and cosine of a small number is equal to 1 because cosine 0 is taken as 1. So when the argument is much smaller, so this cosine function can be approximated as 1. So this function would become equal to 1. You can see from expression here, this cosine omega ct would remain as it is, and AC would remain here, but this cosine beta sine omega mt can be approximated to 1 for the case of narrowband only. Similarly, for sine beta sine omega mt, you can see that sine beta, as we know that sine theta, when theta is much smaller than 1, it can be approximated as theta, approximately equal to theta, when theta goes to 0. So in that case, you can see that if beta is much smaller than 1, in case we can approximate this relationship by simply beta sine omega mt. So theta is now replaced with this beta sine omega mt. This constant AC appears as it is. Sine omega ct would remain unchanged here, but this sine beta sine omega mt would be approximated by this value which is shown here. And you can see that here two sinusoidal functions are being multiplied, and we can convert it into some formula, from product to some formula. You can see that this will be written as cos omega c minus omega mt and cos omega c plus omega mt. Now you should notice that there are again three terms here. First one term is the carrier. Second term is it has the frequency which is carrier minus the message signal omega mt, and third term which has the carrier minus plus the message signal, which is again similar to the AM case. This one is the carrier, this one is the lower sideband, and this one is the upper sideband. However, you can see that here this term is negative, that means the phase will be negative. The phase angle would be negative here, which is illustrated by this negative curve here, just for simplicity. So this one appears to be negative, whereas in AM case it has the positive amplitude. So you can see that this narrowband FM case becomes similar to what we have observed previously, that this has the similar property that it has one lower sideband and one upper sideband, and the carrier which is close to the one that we have observed in the case of AM signals. Okay, so this was under a specific assumption that beta is much smaller than 1. What happens if beta is not smaller than 1? So what is the general case here? So again, referring back to this relationship AC cos omega ct plus phi t, you can see that we can expand it by substituting the value of phi t to be like this formula. You can see this term here, cos beta sine omega mt, is the trigonometric sinusoidal function of a sinusoidal function. Similarly, sine beta sine omega mt, it is also a sinusoidal function of a sinusoidal function. So these two are function of functions. They are also a periodic function with a fundamental periodic frequency of FM. In order to illustrate, I have plotted this first function cosine of sine beta omega mt for different value of beta. So for beta is equal to 0.5, you can see this plot is represented here. For beta is equal to 1, you can see the plot is represented here. For beta is equal to, the plot is represented here. For beta is equal to 5, the plot is here. You can see that these functions are periodic. However, they are not typically sinusoidal, rather they have a different form. From mathematical perspective, these functions, they are represented by using Bessel function. There is a special function in mathematics which is named as Bessel function, or sometimes call it Bessel function of first kind, which is represented by this mathematical relationship. This is the definition of Bessel function, which is represented by this integral from minus pi to plus pi 1 upon 2 pi integral of e raised to j beta sine alpha minus n lambda. You can see that there are two arguments here, n and beta. This n is called order of the function and beta is actually the argument of the function. So these are Bessel function. The trigonometric functions that were shown in the previous slide, this one, these trigonometric functions, they are, when they are expanded in form of a series, so they become a series of Bessel functions, and that series is represented here. Cosine of beta sine omega mt is represented by this mathematical series, whereas the sine of beta sine omega mt is represented by this mathematical series. In fact, both of the series, they can be combined together by using a relationship j minus n of beta is equal to minus 1 raised to r n j n beta. This is a generalized relationship of a beta function. So actually this xct is given by this relationship here, which is illustrated here. By using this property, we can represent xct by this simple relationship which extends from starts from minus infinity to plus infinity, is a simple series. So the coefficients, they are dependent on the magnitude of these Bessel functions, whereas the spectral lines are dependent on omega m. You can see that this is omega c plus n omega m. So for each omega m, there will be a spectral line after every omega m. So you will be having a line after 2 omega m and 3 omega m and 4 omega m and 5 omega m. Similarly, at negative side, you will be having at lines at minus omega m frequency, minus 2 omega m and minus 3 omega m and on. So you can see that the spectrum of the tone modulated signal would appear as a infinite series of lines where the arguments, the amplitudes are dependent on the magnitude of the Bessel function. So this spectrum is represented here. So you will be having a basic Bessel function at the carrier frequency fc. Then there will be first spectral line where you will be having fc plus fm. There will be another spectral line where you would be having fc plus 2fm, and third the line will be at fc plus 2fm, which is dependent on second Bessel function and third order Bessel function, and so on. Similarly, we will be having an spectral lines at fc minus fm and fc minus 2fm and so on. So we will be having these lines. So you can see that these lines, theoretically, they extend up to infinity. So there are theoretically there are infinite number of lines. However, you should notice that the lines, the amplitudes, they are kind of decreasing when you go farther from the carrier frequency. So basically, we can contain the bandwidth to a certain limit, out of which these lines, they become insignificant, and we can restrict our bandwidth to that particular point. So what we have discussed so far is that the spectrum of the FM and PM signal, it depends on the magnitudes of Bessel function. and in order to analyze the bandwidth of FM and PM signal, we need to have look at the number of significant spectral lines which are available in that spectrum. So this is the plot of Bessel function. Actually these are two plots, one with respect to beta for a constant value of n is 0 here, for this curve n is 1, for this curve n is equal to 2, 3 and n is equal to 10. For this case the horizontal axis is n upon beta, whereas the plots are made for constant values of beta 1, 2, 3, 4, 5. You can see that as n increases this beta the magnitude of this Bessel function, it gets decreases, which is also evident from here. You can see that for higher order values of n, the maximum attainable value, it gets decreased. So you can see that the FM spectrum consists of the carrier frequency plus an infinite number of side lines at the frequency of FC plus and minus FM and FM. So there are theoretically infinite number of lines, and these lines are equally spaced by modulating frequency, that is FM. And also you should note that odd order lower side bands, they are reversed in phase. You can see that this J1 and J3, they are reversed in phase, whereas this even order spectra, they are not reversed. Sometimes because we work on the positive frequency line spectrum, so if the spectrum goes in negative, so we need to fold it back in order to get the positive values of the frequencies in the spectrum. So this is the general behavior of the modulated signal spectrum that we observe. At this stage you should notice some of the important characteristics of this Bessel function. There are some important properties that are also listed here. You can see that the relative amplitude of the carrier line J0 beta varies with the modulation index, that is the J0 beta, which is representing the carrier frequency. It is not independent of the message signal. So it actually carries some of the message information. You should recall in linear modulation, the carrier component does not contain the message. However, for FM case, the carrier part also contains a part of the message information. So we cannot remove that carrier component. Secondly, the number of sideband lines, they have relative amplitudes which are dependent on beta. So if beta is much smaller than 1, the only significant sidebands are J0 and J1. For if we try to increase the value of beta, in that case we will be having more number of significant sidebands. So basically the number of significant sidebands which are available in the spectrum, they depend on the value of beta. So the larger value of beta would result in larger number of sidebands. So there in FM and PM case, it's not necessary to have only one upper sideband and one lower sideband. We can have multiple upper sideband and lower sidebands depending on the value of beta. Similarly, because for large number of beta, large value of beta, we would be having significant number of sidebands which will be present in the signal. So we would be requiring a large bandwidth to transmit the FM signal whenever we have large value of beta. So basically the bandwidth of the FM signal is also dependent on this value of beta, which should be which actually determines the bandwidth of the FM signal. So until now we have discussed some important representation related to the spectrum of the FM and PM signals. We tried to represent the spectrum of AM signal and PM and FM signals for narrowband case as well as for wideband case, but with the special condition of tone modulation. With that, we realize that the spectrum is dependent on the values of the Bessel function, which depends on the values of beta. So how many significant number of sidebands would be there? They are determined by the value of beta, and eventually the bandwidth of the FM and PM signals, they are dependent on the value of beta. So this provides a preliminary ground on determining the bandwidth of the FM and PM signal. So for this lecture, we'll stop our discussion here. Inshallah, in our next lecture, we'll be talking about the actual mathematical criteria that we use to determine the bandwidth of FM signals as well as PM signal. Thank you all.